backslash and backslash and backslash and backslash and backslash and backslash and mastering algorithms backslash and backslash and backslash and backslash and mastering algorithms backslash and backslash and backslash and introduction backslash and what is an algorithm? Backslash n types of algorithms backslash n algorithm design techniques backslash n analysis of algorithms backslash n applications in real life backslash n learning path for algorithms backslash n conclusion backslash n backslash n backslash n backslash n backslash n backslash n introduction backslash n. In the world of computer science and software development, algorithms are the backbone of efficient problem solving. Whether you're sorting data, searching for information, or optimizing complex systems, understanding algorithms is essential. This guide provides a comprehensive overview of algorithms, covering their types, design techniques, analysis methods, and real-world applications. Backslash n backslash n backslash n backslash n. What is an algorithm? Backslash n. An algorithm is a well-defined set of instructions designed to solve a specific problem or perform a particular task. It is a step-by-step procedure that can be implemented in any programming language. Algorithms are fundamental to all areas of computing, from simple calculations to advanced machine learning models. Backslash n. Key characteristics of an algorithm include backslash n finiteness. An algorithm must terminate after a finite number of steps. Backslash n. Determinism. Each step must have a clear definition, leading to predictable outcomes. Backslash n. Input. An algorithm may take 0 or more inputs. Backslash n. Output. An algorithm produces at least one output. Backslash n. Effectiveness. Every instruction must be basic enough to be carried out by a human using pencil and paper. Backslash n backslash n backslash n backslash n backslash n types of algorithms backslash n. There are various categories of algorithms based on their functionality and use cases. Here are some common types backslash n sorting algorithms backslash n. These algorithms arrange data in a particular order. Examples include backslash n bubble sort backslash n merge sort backslash n quick sort backslash n insertion sort backslash n searching algorithms backslash n. These algorithms find a specific item within a dataset. Common examples are backslash n linear search backslash n binary search backslash n graph algorithms backslash n used to traverse, search, and analyze graphs. Some notable ones are backslash n breadth first search, BFS, backslash n depth first search, DFS, backslash n Dijkstra's algorithm backslash n Kruskal's algorithm backslash n dynamic programming backslash n. A method used to solve complex problems by breaking them into simpler subproblems. Examples include backslash n Fibonacci sequence backslash n knapsack problem backslash n shortest path problems backslash n greedy algorithms backslash n. These algorithms make the locally optimal choice at each stage, with the hope of finding a global optimum. Examples are backslash n Huffman coding backslash n Prim's algorithm backslash n Kruskal's algorithm backslash n divide and conquer backslash n. This approach divides a problem into smaller subproblems, solves them independently, and combines the results. Notable algorithms include backslash n merge sort backslash n quick sort backslash n binary search backslash n backtracking backslash n used to explore all potential solutions until a solution is found. Common examples are backslash n queen's problem backslash n Sudoku solver backslash n subset sum problem backslash n randomized algorithms backslash n. These algorithms utilize randomness to achieve efficiency or simplicity. Examples include backslash n randomized quicksort backslash n Rabin-Karp algorithm backslash n brute force algorithms backslash n simple but inefficient approaches that try all possible solutions. Examples are backslash n checking all permutations for the traveling salesman problem backslash n algorithm design techniques backslash n. Designing an efficient algorithm requires understanding several key strategies. These techniques help in solving problems effectively and efficiently. Let's explore some widely used algorithm design techniques \n divide and conquer \n. This technique involves dividing the problem into smaller subproblems, solving each recursively, and combining the solutions to form the final answer. A classic example is merge sort, which splits the array into halves, sorts them separately, and merges the sorted halves. \n dynamic programming \n dynamic programming breaks down a problem into overlapping subproblems and stores the results of these subproblems to avoid redundant computations. The Fibonacci sequence is a perfect example where dynamic programming reduces time complexity significantly. \n greedy approach \n the greedy approach makes the locally optimal choice at each step with the hope of finding a globally optimal solution. While it might not always yield the best result, it often provides good approximations quickly. Huffman coding is an example of this strategy. \n backtracking explores all possible solutions incrementally, abandoning paths that do not lead to a valid solution. This technique is commonly used in puzzles like Sudoku and the n-queens problem. \n branch and bound \n this method systematically explores the solution space by pruning branches that cannot yield an optimal solution. It is particularly useful in optimization problems such as the traveling salesman problem. \n heuristic methods \n heuristics are experience-based techniques for problem solving, learning, and discovery. They are especially useful when exact solutions are too slow or impractical. Genetic algorithms and simulated annealing are heuristic methods applied in AI and operations research. \n randomization \n introducing randomness into algorithms can sometimes improve performance or simplify implementation. Randomized algorithms like Quicksort and Rabin-Karp leverage random choices to optimize execution times. \n analysis of algorithms \n before implementing an algorithm. Analyzing its performance is crucial. This involves evaluating both time and space complexity to determine how efficiently an algorithm runs. Understanding asymptotic notation helps in comparing different algorithms. \n asymptotic notation an asymptotic notation describes the limiting behavior of functions as input size grows. Key notations include \n o. N-big O notation represents the upper bound of an algorithm's running time. \n omega. N-omega notation denotes the lower bound of an algorithm's running time. \n theta. N-theta notation provides a tight bound between two functions. \n time complexity n time complexity refers to the amount of time an algorithm takes to run as a function of the input size. For example, bubble sort has a worst-case time complexity of O, n superscript 2, while merge sort maintains a consistent O, n log n, regardless of input. \n space complexity n space complexity measures the total amount of memory space an algorithm needs during execution. In-place sorting algorithms like heap sort require minimal extra space, whereas merge sort uses additional memory for merging. \n amortized analysis n amortized analysis considers the average performance over a series of operations rather than focusing solely on worst-case scenarios. Data structures like dynamic arrays benefit from amortized analysis because insertions and deletions are usually fast except in rare cases. \n empirical analysis n empirical analysis involves measuring the actual runtime of an algorithm through experimentation. This method complements theoretical analysis by providing concrete data on performance across different hardware and software environments. \n applications in real-life \n algorithms play a critical role in numerous everyday technologies and industries. Their impact spans from online shopping recommendations to self-driving cars. Here are some prominent applications n search engines n search engines like Google employ sophisticated algorithms to index web pages and deliver relevant results quickly. PageRank is one such algorithm that determines the importance of web pages based on link popularity. /n/n machine learning /n algorithms form the core of machine learning models, enabling computers to learn patterns from data without being explicitly programmed. Supervised learning algorithms such as decision trees and neural networks classify data accurately. /n/n cryptographic algorithms /n cryptography relies on complex algorithms to secure digital communications. AES, Advanced Encryption Standard, and RSA, Rivest Shamir Edelman, are encryption algorithms that protect sensitive information transmitted over networks. /n/n routing protocols /n network routing protocols use graph traversal algorithms to find optimal paths for data transmission. Dijkstra's algorithm is employed in GPS navigation systems to calculate the shortest route between locations. /n recommendation systems /n online platforms like Netflix and Amazon use recommendation algorithms to suggest personalized content or products. Collaborative filtering and matrix factorization are popular techniques in building effective recommendation systems. /n data compression /n data compression algorithms reduce file sizes for faster storage and transmission. Lossless compression techniques like ZIP and gzip preserve original data integrity, while lossy methods like JPEG compress images with minimal perceptible quality loss. /n artificial intelligence /n AI algorithms enable machines to perform tasks requiring human intelligence, such as natural language processing and image recognition. Reinforcement learning algorithms train autonomous agents to make decisions based on rewards and punishments. /n healthcare applications /n in healthcare, algorithms assist in diagnosing diseases, predicting patient outcomes, and managing medical records securely. Predictive analytics algorithms analyze large datasets to identify risk factors and recommend preventive care measures. /n learning path for algorithms /n mastering algorithms requires dedication, practice, and a structured learning path. Here's a roadmap to help you progress from beginner to advanced levels /n foundational concepts /n start by understanding basic data structures such as arrays, linked lists, stacks, queues, trees, and graphs. Familiarize yourself with fundamental operations like insertion, deletion, and traversal. /n